Uh, Good afternoon, everyone. I want to welcome you to another week. Before we get started today, of course, the midterm two is going to be next week. And let me tell you this, Monday next week and Wednesday will be committed to revision, where I'm going to walk you through some practice questions. Of course, on Friday is when you're going to have um, your midterm. And of course, if you have already put a message on the announcement section about the areas that will be covered in the midterm too, and I need you to be around Monday and Wednesday next week, where we're going to have revision. And I'm also going to tell you some important information about midterm two. I want to welcome you into another statistical topic. Of course, today, depending on time, we're actually going to have two separate lectures. I match them together because um, they are not lengthy. You get what I mean? So I'll first start with this one, type 2 error, probability for a z-test. Before now, let me welcome you to the topic, type 2 error probability for z-test. Before now, you've been introduced to hypothesis testing. Of course, if you want to test if there's an agreement between observed, data and claim, and of course that very claim will come in form of hypothesis. We're actually going to conduct a standard statistical test. And of course, I actually told you the other time, the hypothesis will revolve around parameter. It's going to be a statement, or something I'm going to call an hypothetical statement about parameter. And of course, the only way to investigate whether the claim is right or not is actually to conduct standard statistical tests. And in the process of conducting statistical tests, because of the fact that we acknowledge the fact that model is not the same as reality, there's always going to be error. We cannot do without making error in hypothesis testing. And of course, I actually, told you the other time, we got two types of error, type 1 and type 2 error. Of course, type 1 error is when you reject the non-hypothesis when it is true. And of course, the type 2 error is actually, you're accepting the non-hypothesis when it is false. And let me tell you this, based on what we've done before, when we make an attempt to minimize one error, okay, of course, we're actually going to pay a cost for the other. An example is when type 1, when you make an attempt to minimize type 1 error, that will increase type 2 error. When you make an attempt to minimize type 2 error, that will make type 1 error to go up. Okay? And I made a suggestion the other time, in order for us to minimize both, we need to take a large sample size. And of course, taking a large sample size will have effect on cost. The more people I interrogate, the more resources I'm going to commit to that. That is one of the reasons in the first place why we normally want to investigate a fractional part of the population instead of the whole part. But if a question is asked, which one is worse out of type 1 and type 2 error? I'm going to say that again. If a question is asked between type 1 and type 2 error, which one is worse? A statistician will tell you type 1 error. But let me tell you this. Either of that could be worse, depending on your research content. I'm going to say that again. So the statistician we actually see type 1 error to be the worst one, the one that we need to pay more attention to. That is for statistician. But on average, we want to tell you any of them could be worse depending on your research content. Now, let's say your research content is something that has to do with life. Like, take a look at this. Maybe you will claim maybe there's a problem. Some people have disease, and we're trying to look for a treatment for that. Okay. Now, the null hypothesis is going to support conventional approach use, the treatment, the existing treatment, while the alternative is going to support the new treatment. Now, if the non, I'm talking about clinical, trial now. I'm talking about medical, Now, if we actually fail when the null hypothesis is true, for instance, and it is rejected, the null hypothesis is talking about, oh, we don't need a new drug. If that is rejected, okay, which means you're actually going to be going for, there's going to be new policy, right? There's going to be new treatment. There's going to be new practice. And you're actually going to, government will allocate resources to that. That's a waste of taxpayers' money. Because, that treatment is not effective. But we actually opt for that because of the error that we committed. Does that make sense? So that is a cause. And imagine a good number of patients will be prescribed the drug that is not supposed to be effective. What about side effects? What about some other? That is the cost to pay for that. On the other hand, for type 2 error now, okay, let's say, type 2 error is talking about accepting non-hypothesis when it is wrong, which means what is true? The alternative. Now, the alternative, this time around, is a new drug. Is trying, the alternative is going to say, oh, new drug is effective. Okay. Now, if we make a mistake of rejecting, a medication with high clinical significance, then go ahead. Oh, okay, go ahead. Say it again. Actually, the type 2 error is going to say that you're going against the alternative when the alternative is true. You are actually accepting the norm. You understand now? That's type 2 error. So which means you are supposed to accept the alternative, but you reject the alternative. You are now focusing on the norm. You are in favor of the norm. That's a type 2 error. Now, in this case that I'm explaining now, right? The alternative is a new drug. They've discovered a new drug with more clinical significance. The null hypothesis is maybe placebo or existing drug. Does that make sense? Now, the consequence of type 2 error now is we have missed opportunity to innovate. Does that make sense? Which means a drug that's supposed to improve the symptoms of disease, we've mixed that. You understand? Who is going to suffer for that? Then the patient will suffer for that. What I'm trying to explain is just like which one is worse out of type 1 and type 2 error. But I'm trying to say, depending on your research content, and that was why I cited a medical example. So based on the two scenarios now, both need to be taken care of. Does that make sense? Both need to be taken care of, which means one is going to lead to false positive. The other one is false negative. Whether false positive or false negative, that's not good. Does that make sense? It's just like, let me just take you to another realm. Maybe there was an alarm that a particular country is under attack, and the country now started wasting their ammunition, and they are not even under attack. What has happened? They've wasted resources. So whether false alarm or false negative, false positive, the two, they are actually an alarm that need to be prevented. That's what I'm saying. Does that make sense to you now? So the definition is this: type 1 error is committed when the non-hypothesis is rejected when it's supposed to be accepted. While type 2 error is talking about acceptance of the non-hypothesis that is supposed to be rejected. That is not true. Does that make sense now? Okay, now because of that, we want to focus on, for a particular test now, we want to focus on type 2 error. Because I told you statisticians normally focus more on type 1 error. And that was why you normally, in any test, in statistical test, what you see is alpha. Alpha is the maximum probability of committing type 1 error. Okay, now take a look at this. We are testing hypothesis just like what you said now about the non and the alternative. Take a look at that. The alternative is greater than, you measure something now on type 2 error. Because I told you statisticians normally focus more on type 1 error. And that was why you normally, in any test, in statistical test, what you see is alpha. Alpha is the maximum probability of committing type 1 error. Okay, now take a look at this. We are testing hypothesis just like what you said now about the non and the alternative. Take a look at that. The alternative is greater than, you measure something now, your non-hypothesis equal to, right? Equal to theta naught. And the alternative is a one-sided upper test is greater than, and you need an estimator, right? You need an estimator, a technique that you're actually going to use on the sample, right? Estimator is a function, it's a statistic, it's a function of the random sample. And maybe you take a large sample, and because of that, it's approximately normally distributed. And with the mean of theta and the variance, of course, you have all of that. And don't forget, if you take a look at the side, if you're focusing on proportion, your estimator is going to be pickup, and pickup will follow normal distribution with parameter p and the variance p into 1 minus p divided by n. Okay, but I wanted to take a look at this. Let me first talk about this so that you take a look at this. If I want to test hypothesis on peak on proportion and testing a hypothesis on mean, one depends on parameter, the other one does not. Which one depends on the parameter? It is this guy here. You see that? The one on proportion? You see in the formula for variance, what do you see? In the formula for, I told you the other time, in the variance formula for proportion, we are conducting hypothesis testing. It has to be the parameter, not the sample proportion. But when you take a look at the variance of the mean, okay, the variance of the mean does not depend on the parameter. Which parameter are we talking about? Mu. The parameter, we are focusing on mean is mu, and that is sigma squared over n. Please take notes. Okay, now, if I want to, I believe my Z statistic is going to, the difference between the estimator and the hypothesized value divided by the standard error. Okay, we follow standard normal distribution. It is only when we can establish that we can now, set up our rejection region. Rejection region will be based on the Z statistic. Does that make sense? Rejection region will be based on the Z statistic. Now take a look at this. The other time, I walk you through this. the last lecture, rejection region is Z naught greater than Z alpha. And I walk you through all of that, that your Z alpha is actually this guy. This is your Z alpha, the whole of this. If you your theta, what we're trying to say that theta cap greater or equal to theta naught plus all of that. And the Z alpha, we're going to check that from the table. Okay. And this is the standard error. So when you take a look at what I have here, the only condition to reject is when the theta cap is greater or equal to all of that. And of course, we are able to investigating this, putting into consideration the type 1 error rate, because the Z alpha, that alpha is type 1 error rate. Okay. Now, suppose we are testing that HA. Now, if you now, if you now want to compute the type 2 error, okay, we actually, if you are focusing on type 2 error, we are focusing on a situation whereby the alternative hypothesis is true. Okay. The type 1 error, the focus is actually on when the non-hypothesis is true. Okay. Now, when you take a look at this, and the type 1 error is like, what is the probability, okay, of my test statistic greater than whatever, given that the non-hypothesis is true? If I want to compute the type 2 error, I'm not going to say given the non-hypothesis is true. I'm going to say given the alternative hypothesis is true, and I'm actually going to use the complement of the rejection region. Okay, now what happened now? I want to figure out the type 2 error rate for that. If I want to do that, to the type 2 error as a symbolic representation of type 2 error is beta. Type 1 error is alpha. And type 2 error would be probability fail to reject H naught when theta equal to theta A. You are accepting H naught when it is wrong. Okay, what is right? It is the alternative. Okay, that is that. Now, what am I going to do? I need you to pay attention to this now. What happened? Initially, this sign was greater than. Does that make sense? Initially, it was a greater than sign. Okay, but if I want to compute the type 2 error, I'm actually going to reverse the sign. Don't forget, the greater than sign actually comes from the alternative hypothesis. Okay, alternative is greater than here. Okay, and take a look at this guy. The rejection region is greater than, but here, because we put into consideration the type 1 error, but if I want to compute the type 2 error, I'm actually going to reverse the inequality sign. Then after doing that, if I want to go from the second line to the third line, you know what I'm going to do? I'm going to subtract from this estimator. From the estimator, I'm going to subtract the value under the alternative. What is the value under the alternative? That is theta A. And I'm going to divide by the standard deviation of the value under the alternative. That is when you see sigma cap giving theta A. Does that make sense? That is what I actually going to introduce. That was what I did to both sides. That's what I did. So you can see this guy now. Any question? So to both sides, initially was theta cap. Okay, I'm going to subtract theta A divided by the standard deviation for the standard deviation for the alternative. I'm going to do that to that, and after doing that, when I simplify, okay, when I simplify, I'm actually going to have this guy now, and when I have this guy now, then what have I derived now? This is the probability. This is a type 1 error. Now, if I want to solve that, if I want to go into the example, take a look at this. Please pay attention. Pay attention. Suppose that the vice president in example 10.5, this is from the textbook, want to be able to detect a difference equal to 1 core in the mean number of customers occur per week. Okay, then that is, it wishes to test this. Please take a look at this. The null hypothesis is mu equal to 15. Alternative is mu equal to 16. What is it meaning? It's telling you, if I want to rewrite the alternative, I'm actually going to say mu greater than 15. Does that make sense? If I want to rewrite the HA, I'm actually going to say mu greater than 15 because the value under the null hypothesis is 15. Does that make sense? So greater than 16. Let's say that alternative is 14 now. There's going to be mu less than 15. Does that make sense? Okay. Now, in that case, I will know that my Y bar, the sample statistics follow normal distribution. Okay. And not only that, my rejection region, don't forget, my rejection region will be greater than sign. How do I know it's greater than sign? Look at the alternative. Compare the two values. Okay. Alternative value is greater than 15 by 1. There, it's telling us the alternative is actually going to be an upper tail. Any question? Okay, when it's an upper tail, take a look at the rejection region now. Now, what do we want to find? We want to find beta. We want to find type 2 error. If you want to find type 2 error, you need to first derive the rejection region. When this rejection region is actually constructed, putting into consideration, you see alpha, right? Putting into consideration type 1 error. But I want to figure out type 2 error now, which is beta. What I'm going to do is I'm actually going to use the complement of this. Okay, now I'm going to show by picture now. Take a look at that. Do you see picture in blue? You see picture in red. Okay, both the null and the alternative hypothesis, they are actually going to follow the same distribution. Normal, except that what is different between them? They have different means. One is saying mu equal to mu naught. The other one is saying mu equal to mu A. Just like in this question, 15 and 16. Does that make sense? Now, if you take a look at the shaded area, you can actually see the type 1 error rate and you can see the type 2 error rate. Take a look at all of that. Now, what do I want to find? I actually want to find beta, which is the type 2 error rate. I told you it's also significant. I mean, we need to also pay attention to type 2 error, not only type 1 error. If you want to go by my illustration the other time, using the numerical feed example. Now, what is the beta? What is type 2 error? Probability fail to reject H naught, given that the alternative is true. Does that make sense? You fail to reject H naught, given that, which means you are accepting H naught. Let me tell you, in statistical analysis, we don't say accepting H naught. We normally say we fail to reject. Does that make sense? We don't say accept. Okay, now what is going to happen now? Go to the second line. Look at the second line. What happened in the second line? I was able to reverse the rejection region. Initially, the rejection region was what? Greater than sign, right? Now, this is going to be less than sign, and I'm still going to write all of that, but I'm going to say given, I'm only focusing on the hypothesized value under the alternative. Does that make sense? Now, if I want to figure out the probability now, okay, what I'm actually going to use is the formula here. So which means the probability of Z, that's 0, 1 normal means Z, less than mu naught minus mu A. Okay, mu naught minus mu A. You know the difference. Don't forget, this man wants to detect the difference. I told you the other time, $5.1 million, $5 million. Somebody could say, there's no difference. The little is little, but not in terms of $5.1 million and $5 million. The only way to detect a statistical significant difference between two numbers is to conduct a standard statistical test, not just by looking at the numbers. Does that make sense? Okay, now, if you take a look at this guy now, that is the formula we're actually going to use. Now, let us now substitute based on what you're giving, right? you'll be given the mu naught to be 15, the value under the null hypothesis. Mu A is 16, the value under the alternative. And, all what you just need to do is to plug them in. Okay? 15 minus 16. Okay? And of course, the 3 here is actually going to be, I think you're going to be given the variance and the standard deviation. I think they're going to give you, if you check 10.5, okay? So that means the standard deviation was actually 3, okay? And the square root of 36, the sample size, okay? And how do I get 1.645? Come back here. The Z alpha, okay? Z alpha, which is 1 minus, if you want to check from the table, that's going to be 1 minus alpha. Or if you want to check from R, Q norm into 1 minus alpha, that will give you 1.645. Now, you have that guy now. Okay, by the time you simplify all of that, you're going to find yourself here. Okay, now when you find yourself there, you can actually check from table, normal table for negative. Okay, or you do P norm in R, P norm of negative is 0.3555. Okay, if you don't want to do that, okay, the negative less than is the same thing as positive greater than, which is going to be 1 minus P norm of the positive numbers. And in the end, okay, that is actually giving you this result, 36%. 33% is very huge. That was why I said this is a fairly large type 2 error rate. Even though the type 1 error was small, the type 1 error for this was 0.05, but the type 2 error is very, very huge. And I told you the other time, the way to minimize, I said how to control type 1 and type 2 error. What are you going to do? You should be ready to increase your sample size if you really want to minimize the two. Okay, but without that, when you make an attempt to minimize one, okay, you're actually going to maximize the other. Okay, now this is the situation. We've just talked about increasing sample size, right? Now the question now is, one of the way to actually attain control is maybe we can control them by trying to figure out what would be the minimum sample size I need to take in my research if I want to control the 2 error. Does that make sense? And that is what I want to do now, is sample size selection. What would be the number of samples that I need to select, okay, number one, to be able to detect difference, and not only that, to be able to, bring, to minimize both the type 1 and the type 2 error. Okay, and you know what I want to do first? If you take a look at this, the type 2 error rate was very high, but the type 1 error rate was very, very small. Okay, maybe one of the ways to solve the problem is, let me first know the number of sample size that I need to choose if I really want to, if I desire a particular type 2 error and a type 1 error rate. Does that make sense? Now, what I want to do now, let's go back to testing this hypothesis again. I need you to focus on this. Your testing hypothesis, okay, it's a one-sided, it's an upper t-test. You can take a look at the alternative, mu greater than mu naught. Of course, don't forget, before you can use a z-test, the sampling, the distribution of the y bar has to be normal, okay? And the rejection region, it's actually going to be y bar greater or equal to k. K is all those, k here is this. I'm going to show you what k is, so that I don't, the whole of this. That is your k. Does that make sense? The whole of that is the k. Does that make sense? Okay, now, if the whole of that is k, now, we know that the rejection region for short test is going to be that. Now, let us first calculate, for instance, how do we calculate type 1 error rate? If I know my type 1 error rate, right? if I set up a type 1 error rate to be a particular value, I can decide to figure out what is the minimum number of sample size do I need for me to be able to desire that for that value of type 1 error rate. Of course, all what I'm just going to do to equate this guy to alpha. If I equate that to alpha, if I know my K, I know my mu naught, I know my sigma, I will be able to determine my sample size. Does that make sense? Okay, and because this guy here, that probability will be equal to alpha. Does that make sense? And in a way, you're going to use inverse normal. Okay, now take a look at this. I can do the same thing for type 2 error rate. What am I going to do if I want to do the same thing for type 2 error rate? Take a look at this. Instead of y bar greater, I'm going to take the inverse of that. It's going to be y bar less than k. Given I'm referring to the alternative, then I will go all the way. Based on this now, I'm going to equate this guy to what? What am I going to equate that to? Beta, right? I already know the particular beta that I want, but what I want to figure out is what? What I want to figure out is the sample size. Now, take a look at this now, which means one equation to determine alpha, another equation to determine beta. But take a look at this. I now said, in order that type 1 and type 2 error rate control at the value alpha beta, then we should be ready to solve two equations. Does that make sense? Because we want to control both alpha and beta, which means we actually are going to come out with a value that we want to set for alpha and for beta. So if we want to do that, we should be ready to solve these two equations simultaneously. Who doesn't understand that? The probability of a z-score greater or equal to that guy will be equal to alpha. That's type 1 error. The second one, the probability of a z-score less than that is going to be equal to beta. Before I go into this, I already know my alpha. I already know my beta. My daughter in high school, at times when she comes home, she's doing algebra 2. And you're going to say, my dad, what is the meaning of all this solving system of equation, this, that? Now, you know the essence now. Okay? You know the essence. I told my daughter, these equations, they depict reality. Okay? They actually formulate, they converted, real world, real situation, real life situation into mathematical expression. Just for us to be able to solve the situation mathematically, we need to convert into mathematical language. Without the knowledge of algebra, there's no way we're going to move forward. If we really want to obtain, what would be the sample size? If you take a look at here, sample size n in the first one, sample size n in the second one, and I've already set my alpha and beta, so which means whatever the value of alpha and beta, the type 1 error and the type 2 error, the probability of type 1 error and the type 2 error you set, you will be able to solve this mathematically. What would be the sample size that you need? And why do we say that? Because we know controlling for type 1 and type 2, you need to take more sample. If I want to take more sample, how large is the large? Does that make sense? And that's what we want to find here. Now, if you take a look at this, if I want to remove the probability value, then I'm going to equate that guy to z alpha and to negative z beta. Please take note. To z alpha and to the negative z beta. And don't forget, from any of the two, okay, you're actually going to see k is going to be the same. Like from here, if you take a look at this guy now, from this guy, right, k is going to be equal to this. From here, k is also going to be equal to that. Then we can equate them. When we equate them, what are we looking for? We're looking for sample size. We need to put into consideration the knowledge of algebra here, solving for n, which is the sample size, solving for n right now, I'm actually going to get this guy here. If you want to determine your sample size now, that is the formula to use, which means in the formula, I need to check from the table Z alpha, Z beta, because of course you already know you are going to be the one that will set your value for alpha, the value for beta. Then I need to know the sigma squared. Then I need to, of course, I know the mu A and the mu naught. Any question on that? But don't forget, look at what I put. For every n greater than or equal to n, what do I mean? If I have a sample size n, okay, maybe 40, and I have another sample size that is greater than that or equal to that, what is going to happen? The type 1 error rate will be less or equal to alpha, and the type 2 error rate will be greater or equal to beta. Now, I'm going to walk you through an example now. Now, this is so what I'm trying to say now, this formula now will give you the smallest sample size needed. Smallest sample size needed. Okay? If you set up your alpha and beta, don't forget, I told you the other time, if you really want to control both type 1 and type 2 error, of course, you should be ready to increase your sample size. And the question now is, ready to increase my sample size, what is the minimum required? The formula here is actually, that's what you're going to use. But there's a remark here. The sample size is an increasing function of sigma squared. Why? Because sigma squared is in the numerator, right? Sigma squared is in the denominator. Whatever that is in the denominator will be a decreasing. Take a look at that. Okay? And n is a decreasing function of what? Of mu A minus mu naught, because the mu A and the mu naught is in the denominator. Does that make sense? Okay. Now, the difference in mean that we actually want to detect, which means if the difference in mean that we want to detect is very large, okay? If the difference in mean that is, if that is very large, then the sample size is going to be a decreasing function, okay? And n is a decreasing function of alpha, beta, okay? Your desired error rate. And of course, we have a remark here. Minimum sample size for a lower tail test is the same, okay? So where you know, here I actually derived this formula, putting into consideration when the alternative is an upper tail. Even when the alternative is a lower tail, it's still going to be the same. But no closed form solution for a two tail. If your alternative is two tail and you actually want to determine your sample size, your equation will not be in a closed form. Okay? And that means we need to, if you want to solve the equation that are not in a closed form, then we have to go numerical. You know, in mathematics, that's what we call numerical approach. Whether we're going to go by way of iteration. Does that make sense? That is for two-sided tests. Okay, now I'm gonna walk you through an example right now. Take a look at this. Suppose that the vice president, you know, in the example 10.5 want to test mu equal to 15 and against mu equal to 16, and alpha beta equal to 0.05. You set them, right? You set alpha and beta to be that. Those are minimum, those are very, very small. They are reasonable, right? You set them and you want to find the sample size. Okay, what is the minimum? You find the sample size that will ensure this accuracy, and your variance has to be known. You have to, assuming that sigma square is approximately 9, all what you just need to do is to make use of this formula. Okay, plug in all those values. Okay, Z alpha, Z beta, plug in all those values, and at the end of the day, you're actually going to round up 98. Okay, it means if you desire type 1 and type 2 error rate to be 5%, then the minimum sample size you need to be able to dictate if there's any difference between the known and the alternative is actually, you need 98. Now, we can ask some questions. Okay, what if we're using different value for type 1 and type 2? Like, we now want to see the effect. For it, what has happened here is that, you know, initially, alpha equals 0.05, beta equal to 0.05. If we want our alpha to still be 0.05, but we increase the beta, what effect is it going to have on the sample size? If you compute that, okay, the sample size is going to go down. Look at that. Okay, from 98 to 78. When you retain the type 1 error rate, but you decide to increase the type 2 error rate, increasing type 2 error rate, then it means the sample size required will be smaller. You save money, but at the expense of efficiency. You know, in research, we are faced with two things in research: efficiency and reducing costs. Does that make sense? It's not only efficiency we're about. We also want to reduce cost. So when I just demonstrated now, if type 2 error, if you increase type 2 error, if you increase that, then the sample size is going to come down. Now, what if in this situation, let us now let's look at the effect of, you know, when the alternative is decreased. You know, initially it was 16. And alpha and beta stay the same at 0.05. Okay. What, you know, when that is decreased, what has happened? The gap has decreased. Okay. When the gap has decreased, then you need so many sample size. I said it the other time in this class. When you are using small sample, you may not be able to detect a difference, even if difference exists. You remember? I said it in this class. Even if difference exists between two groups, but if your sample size is small, okay? Now, when you take a look at this now, situation where the null and the alternative is very close, for you to detect a difference, you need a very large sample size. Look at that, 390. Okay. Now, let us now consider another thing. Let's look at the effect of variance. Initially, okay, it was actually 9. And when the variance goes down, instead of 9, the variance goes down. And if the variance goes down, what do we have? That is 390. The variance goes down, but the alpha and the beta is still 0.05. Okay. And you know, initially we said, what do we, you know, when you talk about sample size is expected to be an increasing function of the variance. The variance is in the numerator. And that is why you see that as high. Does that make sense? Take a look at that. Any question? I'm done with the first. I'm done with it. Any question on this?